Hello everyone. In this video, I'm going to talk about the second derivative test that we use to find maxima or minima of a function. Before we jump on to second derivative test, I would like to discuss the relationship between the original function, the first derivative, and the second derivative. And I'm going to do that through a graph here. So let's say we have this graph of any function fx. Then we're going to try to draw a graph of derivative of this function. So I'm going to choose color blue for the derivative graph. And we notice that first the slope is decreasing, right? So it's negative. And then at one point it becomes zero. So slope is negative and then it becomes zero where we have the point of minima because here the slope becomes horizontal and then it becomes positive and there comes a point when it becomes maximum in between. So let's say, so here we have the most steep curve, so maximum, and then it's gonna start decreasing again and then it's gonna become zero at this point. So again it's gonna become horizontal at the maximum point and it's gonna be zero again. So this is the function f prime x, which is our derivative function. So the point where our slope of original function becomes zero, I'm going to call them critical points. So these are two critical points in this case. So now we're going to look at our first derivative curve, which is the blue curve, and we're going to try to draw a diagram for our second derivative of fx. If we notice this curve f prime max, we notice that first the slope is increasing. It becomes maximum about here, and then it comes a point where the tangent, it becomes zero. So that is zero, and then it starts decreasing. So I'm just gonna go ahead and redraw this curve. All right, folks, so my three curves are ready. So first we have red one, which is our original function. And then blue one is our first derivative, so the graph of the slopes of original function. So we notice that it becomes zero here, and zero here. So I just extended my curve. And then I also drew the graph of second derivative. So that is the graph of slopes of my blue curve. So we notice that first the slope is positive, but it's decreasing. And then there comes a point when slope becomes a zero. And then again, it's negative. And then there comes a point when again it becomes zero because we got a point of minima here. And then it keeps on increasing. So few observations that we can make from here is, so let's look at the critical points. So critical points are the points where first derivative is zero. So this point is a critical point, this point is a critical point, and this point is a critical point. So these are the points of maxima or minima of the original curve. And we notice that, so at critical point, first derivative is zero. And the second derivative, what is the sign of second derivative here? So sign of second derivative is positive. So we get a point of minima. Similarly, if we look at the second critical point, again here the first derivative is zero. And if you want to take a look at the sign of second derivative, so at this point, second derivative is negative. And for our original curve, this was a point of maxima. And the discussion goes on. So now I'm going to tell you quickly what the second derivative test is. So second derivative test tells us about point of maxima and minima, and it also tells us about the concavity of the function. So if the curve looks something like this, facing downward, so we call it concave down. So this is concave down, it's facing downwards. And here the second derivative would be negative for this portion of the function. So the critical point would be here, right? So maximum, so slope is zero because it is horizontal. So this is your critical point. And we notice that the slope on this side is positive. It changes from positive to negative. And here our second derivative is going to be negative. So concave down. So you can always So when you're feeling down, right? So that is how you remember concave down. And the second derivative is negative. So negative mood. Similarly, if you have something like this, then the curve is called concave up. So concave up. And the second derivative for this curve is going to be positive, and the critical point at critical point, right? So this is your critical point where slope is 0. So here the first derivative is 0, but the second derivative is going to be positive. And a way to memorize this is you can always, like, when you're feeling positive or when you are cheered up. So concave down means negative, concave up means positive. Second derivative positive. And now I'm going to ask you a question. So if an interval contains one critical value, let's say x is equal to 0.5, and we can plug in this critical value in the second derivative, and we get a negative value in the end. So you need to answer me whether that's a point of maxima or a point of minima. So if we look at that, like if we get a negative value, so that means our curve is concave down. So concave down, right? So what kind of point we get here? So we get a point of maxima. So the answer should be, we're going to get a maxima. So second derivative negative means you get a point of maxima. It doesn't seem very intuitive, but it's the opposite way. So if it is negative, it means concave down. So that means you get a point of maximum value at that point. So from this, we learned that second derivative test is quicker to find maxima minima if it's easier to differentiate the function again. And the gist of this discussion is, so if at critical value your double derivative is negative, then you get a point of maxima. If at critical value the value of double derivative is positive, so which means concave up, which means you get a point of minima. So that is how we use our second derivative test. Another advantage of second derivative test is it tells us about the inflection point. So inflection point is the point where the concavity of the curve changes. So we're going to discuss the concavity of the curve in relation to second derivative test. So concavity changes means it changes from being concave up to concave down. So if we look at our original function, so here it was concave up to this point, and then it starts becoming concave down. So concave up here, and then concave down here. And we notice that, so there is a point in the middle, so where it changes concavity, where the slope is maximum or where it is maximum steep. And if you notice, even at that point, we also notice that, so that is a point when our second derivative is 0. So at this point, second derivative is 0. So this is called inflection point. So where the curve changes its concavity, so that point is called inflection point. Similarly, the next inflection point would be somewhere here where it's maximum steep, and again where the second derivative is 0. So that would be your another inflection point, because the curve starts being concave up after this point. So again, here the curve is concave up. So second derivative test also helps us to find inflection points. So in this graph, all these points corresponding to here, they tell us about the inflection point. So these values of x. So these are our inflection points, and we can notice that, and there will be one here as well. So these 3 points are inflection point. We can notice that the curve is concave down before this point. In other words, also the second derivative is gonna be negative in this case. And then from here to here, the curve is concave up. So concave up, and the second derivative is gonna be positive. Again, in this interval C, so it's gonna be concave down. The second derivative is negative in this case, and after in region D, again we have concave up. The second derivative is positive. So basically the inflection points are the points which separate the concave up to concave down. So these are the points where the curve changes its concavity or changes its behavior from being concave up to concave down, or from being concave down to concave up. And at all these inflection points, the double derivative is going to be 0. So f double prime x is 0. So second derivative of the original function is going to be 0 at inflection points. Let's take a look at the summary of second derivative test. So find first derivative and second derivative of the given function. And find the critical value. For critical values, we set first derivative equal to 0 and solve for x, or also we find the values where first derivative does not exist. And then we plug in those critical values in the second derivative function, and we look at the sign. If the sign is positive, we say that it's a relative minima. If sign is negative, we say that it's a relative maxima. And if you get the value 0, then second derivative test is inconclusive. So you need to use first derivative test in that case. So use first derivative test that I discussed in the previous video. So I hope that makes sense. So we only use the second derivative test in the maxima minima problems when the second derivative is easy to compute. Let's do this example, and we're going to use the second derivative test in this one. Find the maxima and minima for this function. So function is given. So first we're going to find the first derivative. So that would be 9x squared minus 12x. And we're also going to find the second derivative. So 9 times 2x, which is 18x minus 12. All right, so our next step is to find the critical values. So for the critical values, I'm going to set my first derivative equal to 0. So this implies 9x squared minus 12x equal to 0. So take any common factors out. 3x is a common factor, so 3x minus 4 inside, so that is equal to 0. So either x is 0 or 3x minus 4 equal to 0, which means x is equal to 4 over 3. Since in this case it was easier to find second derivative, so next we're going to decide on our max or min. So we're going to use second derivative test for the same. So I try to find my second derivative's value at the critical value. So first I'm going to plug in x equal to 0. So we get 18 times 0 minus 12. So which is negative 12. So I get a negative value. So second derivative negative means, so that's how I always do it. So the second derivative negative means concave down, right? And so what we get in this case, maxima or minima? So concave down, it means we get a maximum value. So we get a maximum at this point. Similarly, if I plug in x equals to 4 over 3, so I get 18 times 4 over 3 minus 12. So when I solve it, I'm going to get a positive value. So positive value means concave up, right? So concave up. So what we get in this case, concave up. So this would be a point of minima. So we get the maximum value at x equal to 0 and minimum value at x equals to 4 over 3. And now we can plug in these values in the original function and find our maximum and minimum height for the function. Therefore, for the given function, This one is our given function. So the maximum value will happen at 0. So we get 3 times 0 cube minus 6 times 0 plus 4. So maximum value is 4. And the relative minimum value is going to happen at 3 over 4, 4 over 3, sorry. So f of 4 over 3. So you're going to plug in all the values in the original function. And you will see that in the end you get, so let me calculate this. So we get 4 over 9. So this is our relative minimum value. So relative maxima is 4 and relative minima is 4 over 9. I hope that makes sense. So we use the second derivative test to find the maxima minima in those problems where it is easier to differentiate again. So in the next video, I'll do a curve sketching question in which I will try to use the second derivative test. And make sure you also watch that video as well. I hope you enjoyed this video and I'll see you next time again. Bye for now.